What's up, everybody? Welcome back to Mathlete's Corner. In this video, we've got some more juicy competition problems because I'm getting the vibe that that's what y'all like to see. So in this video, we have the first two problems from the 2025 ARML Indivs. So in the next couple of videos, we're going to be continuing with this competition. So that'll be about 3 more videos after this one. And that'll bring us to the weekend right before the AMCs. So I may or may not drop an AMC review video, but we'll worry about that when we get there. Let's get right into these problems. So problem 1 is compute the least integer n for which n factorial over n plus 3 times n plus 4 times n plus 5 is an integer. Well, for this to be an integer, our number one constraint is that n factorial has to be greater than n plus 3 times n plus 4 times n plus 5. Because otherwise, not only will it not be an integer, it'll actually be less than 1. So that's no good. So after some testing, you'll notice that 6 factorial is actually less than 9 times 10 times 11, right? Because the left side is 720, the right side is 990. But 7 factorial, which is 5040, is greater than 10 times 11 times 12. So we can start checking from 7. So when we test for 7, we get 7 factorial over 10 times 11 times 12. Now we notice this denominator has that pesky 11. And we don't have an 11 in the numerator because we only have the integers up to 7. So for that reason, 7 does not work. And we'll notice that with 8, we have a very similar situation because our denominator is 11 times 12 times 13. The 11 makes this not an integer. Now you'll also notice that here we have a 13. So for that reason, 9 and 10 will also not work because for both 9 and 10, you'll have that 13 sitting there in the denominator. So finally, we can test for 11. So when we do that, it's 11 factorial over 14 times 15 times 16. And at first sight, this looks promising. So let's check it out. We have 11 times 10 times 9, 8, 7, 6, 5, 4, 3, and 2. So we get a 14 from here. We get 15 from here. And we can get 16 from the 8 here and one of the 2's from the 4. So for that reason, when n is 11, this is an integer. So our final answer is 11. On to the next problem. That's problem 2, which reads, compute the number of ways in which an 87 by 1 grid can be fully tiled with rectangles of size 8 by 1 and 7 by 1. So essentially all we're looking for is how many ways can we combine a bunch of 8s and a bunch of 7s to add up to 87. Well, the initial natural way to think about this is, let's start with 10 times 8 plus 7. Classic, base 10, natural way to go about this. Now we have to see, are there any other combinations, any other number of 8s and number of 7s that will eventually add up to 87? Well, we can notice if we reduce this 10 here by 7, and why am I doing that? So that we reduce the total sum by 56, and we're essentially replacing 56 of our tiles that we counted with 8s. Now instead we want to count them with 7s. So when we do that, instead of having just one 7, we'll have 8 more 7s. So we will have a total of 9 7s. And feel free to double check that this is equal to 87. So now that we know that we can either have 10 8s and 1 7, or we can have 3 8s and 9 7s, this just comes down to how many combinations do we have to rearrange our either 10 8s 1 7 or 3 8s and 9 7s. So our 10 8s and 1 7 is fairly more straightforward because we have a total of 11 tiles and we want to see how many ways we can rearrange them. Now 10 of those 11 tiles are congruent, so essentially it's just 11 choose 10, which comes out to a total of 11. Now, similarly here, we have a total of 12 tiles. 3 of them are congruent, 9 of them are congruent, so this comes out to 12 choose 3 ways, which is 12 times 11 times 10 all over 6. So after some cancellation, that comes out to 220. Now when we add 220 and 11, we reach our final answer of 231. That's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next week here at Mathlete's Corner.